Okay, so let's unpack this today. I've been looking at this research on high-feed milling from ISCAR, and I gotta be honest, my initial reaction was, well, it was pure skepticism.
Yeah, it's completely counterintuitive when you first read it.
Right, because I want you to imagine you have a solid block of steel and a deadline. You need to turn that block into a pile of chips as fast as possible. My instinct, and I think, the instinct of most people, is to grab the biggest, heaviest tool I can find, bury it deep into the metal, and just push until the machine groans.
The classic brute force method.
Exactly. But the source material we're looking at today, this technical documentation called ISCAR High-Feed Milling Engineering, the Productive Edge, it argues the exact opposite.
Right, they're basically saying stop digging deep. If you want to go faster, you need to take much, much smaller bites.
And I'm sitting here thinking, if I'm taking smaller bites, aren't I just going to be standing in front of the machine for 10 times as long?
That is the logical assumption. But the key isn't just the size of the bite, it's the speed of the chew.
So that's what we're doing our deep dive into today. We're going to figure out the engineering behind ISCAR's high-feed milling tools. Specifically, we have details on systems like Logic 4 feed and Halide do feed.
Right.
We're basically on a mission to unpack how shaving off tiny little slivers of metal actually results in massive productivity gains. And more importantly, why this weird geometry solves that constant trade-off between productivity and stability.
It really is a fundamental shift in machining strategy. We're moving away from that era of heavy, slow brute force and entering an era of fast, light, almost aerodynamic machining.
Aerodynamic machining, I like that. But let's start with the basic physics here, because I really need to wrap my head around this shallow cut concept. In the conventional days of milling, how are we attacking the metal?
Conventional milling relies on what we call deep axial engagement. You take a tool, say a standard end mill, and you engage a significant portion of it side the flute length against the material.
So you're taking a really heavy radial width of cut.
Exactly. It's like trying to shovel heavy, wet snow by digging the shovel all the way to the bottom. Because you have so much contact area, the resistance is massive.
Right.
You generate a ton of heat, a lot of friction, and you just need a massive amount of horsepower to shear that metal off. And because the load is so high, you have to move slowly. If you move fast with a cut that deep, you just
snap the tool instantly.
You'd snap it instantly.
Okay, so that's the tank approach. Slow, heavy, lots of torque. How does ISCAR change this picture?
Well, they basically flip the equation entirely. Instead of a deep cut, they use a very shallow depth of cut. We're often talking less than a millimeter or two.
Wow, that is shallow.
But, and this is the critical part, because the cut is so light, they can run feed rates that are effectively off the charts compared to those conventional standards.
Okay, but I'm still stuck on the math here. If I reduce my depth of cut by a factor of 10, don't I have to move 10 times faster just to break even on metal removal? Is that even physically possible without the machine just shaking apart?
It is, and this is exactly where the geometry comes in. It's not just about moving fast. It's about the angle of attack. The magic number in ISCAR's designs is the entering angle.
Right, I saw that mentioned.
Yeah, in a standard face mill, that angle is usually 90 degrees or 45 degrees. But in high-feed milling, it's incredibly low, typically between 10 to 20 degrees.
10 degrees? That seems incredibly shallow. You're barely engaging the material at all.
You are, but that low angle creates a phenomenon called chip thinning. This is the core concept you have to grasp to understand why this works.
I see chip thinning mentioned about a dozen times in these documents. And to me, a thin chip sounds bad. Doesn't a thick chip mean I'm removing more metal?
In conventional thinking, yes.
Yeah.
But here's the physics trick. When you approach the metal at a 90-degree angle, the chip thickness is exactly the same as your feed rate per tooth. It's a 1-to-1 ratio.
Okay, 1-to-1 makes sense.
But at a 10-degree angle, you can push the tool forward, meaning increase the feed rate dramatically. But the actual thickness of the chip being sheared off remains quite thin.
So you're basically tricking the tool. You're moving the tool forward, say 50% faster, but the tool thinks it's doing the same amount of work.
Precisely. You're effectively spreading the chip load over a much longer section of the cutting edge. This prevents the edge from overloading. But there's a second benefit to chip thinning that is arguably even more important, specifically regarding thermodynamics.
Thermodynamics. Okay, now we're getting into the weeds. Why does a thin chip matter for heat?
Because in machining, the chip is your heat sink. A thick chip holds heat, but it also takes time to form. If you're cutting slowly with deep cuts, that heat has time to soak right into the tool and worse into the workpiece.
Which is obviously bad.
It's catastrophic for tool life. But with high-feed milling, because you are generating these thin chips at incredible speeds, the heat is ejected almost instantly. The heat is in the dust, basically. It flies away before it can transfer into the cutter.
So it's basically a heat evacuation system disguised as a milling tool.
That is a perfect way to describe it. You are literally outrunning the heat.
Okay, that explains the speed part of the paradox. But let's talk about the machine itself. I was reading the section on force direction in the source, and this felt like a huge deal for anyone who actually owns a machine shop.
Oh, absolutely.
Because usually going fast means vibration, it means chatter, it means that screaming noise that makes you want to cover your ears and leave the building.
We have all heard that sound. That is the sound of radial force.
Radial meaning sideways, right?
Yes. In conventional milling, especially with those deep cuts, the primary force is pushing sideways against the tool. Imagine holding a long stick and pushing the tip sideways against a wall. The stick bows right.
Yeah, it deflects.
That deflection is what causes chatter. It's inherently unstable. And it's absolutely brutal on your spindle bearings. That sideways pushing is constantly trying to pry the spindle shaft out of its housing.
So even if the tool itself doesn't break, I'm slowly killing my machine over time.
Exactly. You're wearing out the bearings, you're stressing the ball screws. But ISCAR's high-feed milling changes the direction of that force entirely. Because of that 10 to 20 degree angle we talked about, the majority of the cutting force isn't radial anymore, it's axial.
Axial, so pushing up.
Pushing straight up into the spindle, up into the z-axis.
So instead of trying to bend the stick sideways, you're jamming it straight back into your arm.
Exactly. And machine tools are incredibly rigid in that direction. The spindle is designed to take massive compression loads. By directing the force axially, you virtually eliminate vibration.
This was a major aha moment for me. If I'm a shop owner, ISCAR is basically telling me this strategy isn't just about cutting faster, it's about not destroying my $200,000 machine in the process.
It goes even further than that, actually. This axial force concept revitalizes older machines.
How so?
Well, let's say you have an older mill. The bearings are a little loose. The rigidity just isn't what it used to be. If you try to run a heavy conventional cut, it's going to chatter like crazy. It just can't handle the side load anymore.
Right, it's worn out.
But if you switch to a high-feed strategy, you are pushing the force up into the solid column of the machine. The slop in the bearings suddenly matters a whole lot less.
You can take a 20-year-old machine and achieve metal removal rates that compete with a brand new machine just by changing the tool geometry.
Exactly.
That is a fascinating economic angle. You don't necessarily need a new engine, you just need better tires.
Or a much better driving strategy.
Right. And speaking of strategy, the text mentions specific tools like the chatter-free damped tool holders. I assume these are for when things get really tricky.
Yes. Because even with the axial force benefits, sometimes you have to reach deep into a cavity. You have a long tool overhang.
Which is usually a total nightmare for vibration.
It acts exactly like a tuning fork. But the combination of the high-feed geometry directing the force up and the damped mechanism in the holder itself means you can run stable cuts at lengths that would be, frankly, impossible with conventional tools.
Okay, so we've got stability covered and we've got the physics of heat. But at the end of the day, this is a business. We need to talk about efficiency and the bottom line. The source material brings up the logic for feed system. It sounds very futuristic, but what is the actual practical benefit here?
Logic 4 feed is a great example of the economic engineering ISCAR is doing. It uses a specific insert shape. Often it's a twisted geometry to fit that precise high feed angle. But the logic part really refers to the cost per edge. These inserts are double-sided and they have 4 cutting edges.
4 edges. So if I burn one out, I just flip it and then rotate it.
Exactly. It maximizes the material usage of the carbide itself. But the real economic gain comes back to that metal removal rate. The documents explicitly state that despite the incredibly shallow cut, you can achieve removal rates several times higher than traditional milling.
Several times higher. So we're talking 300%, 400%.
Yeah. Easily, depending on the specific material. And think about your spindle utilization. If you are roughing out a part, and it usually takes an hour, and this high feed milling can do it in 20 minutes, you have just opened up 40 minutes of machine time to make an entirely different part.
That's the holy grail of manufacturing, but I have to play devil's advocate here for a second. If we are running these feeds sometimes hundreds of inches per minute, surely we are burning through these inserts way faster. Friction is friction, right? Am I saving time on cutting, but just losing all that money buying boxes and boxes of inserts?
That is a very valid fear.
Right.
But remember the heat evacuation we discussed earlier. That thin chip protects the edge. However, ISCAR doesn't just rely on physics alone. They rely heavily on chemistry. The material science here is critical. They list specific advanced carbide grades in the documentation. IC830, IC882, and IC8808.
IC882, what exactly makes these grades special? It's just carbide, right?
It is never just carbide. These grades are engineered with tough substrates, and they're coated with very specific layers, usually PVD or physical vapor deposition.
Okay, pause there. I see PVD and CVD on toolboxes all the time. Why does PVD matter specifically for high-feed milling?
CVD, or chemical vapor deposition, is a great coating, but it tends to be thicker. It's incredibly tough, but it rounds the cutting edge slightly during the process. PVD coatings are much thinner. They allow you to maintain a razor-sharp cutting edge.
And because we're slicing such thin chips, we really need that extreme sharpness.
Exactly. You need a sharp, clean shear. If the edge is too dull, you start plowing the metal instead of cutting it. That generates heat and defeats the entire purpose of the geometry. The IC830 and IC882 grades use this PVD technology to stay incredibly sharp while still being tough enough to handle the constant impact of hitting the metal 1,000 times a minute.
Wow. And what about the wear pattern? The text specifically mentions predictable wear. Why highlight that?
Because in conventional milling, failure is very often catastrophic. You're pushing the tool so hard that when it finally fails, it just snaps. It ruins the part, and it might even damage the spindle.
The big bang that stops the whole shop.
Right. It's terrifying.
But with high-feed milling, because the forces are much lighter and they're distributed, the wear is gradual. You can literally see it coming.
So I can say, okay, this insert historically lasts 45 minutes, and I'll just program an automatic change at 44 minutes.
Exactly. It allows for what we call lights-out manufacturing. You can actually trust the process enough to hit cycle start and walk away from the machine.
That trust is really put to the test, though, when we talk about the impossible materials. The source material lists a real rogues gallery of metals that usually kill tools. Hardened steels, stainless steels, titanium, inconel.
The heat-resistant superalloys.
Yeah. I hear inconel and I immediately think of a material that just hates being machined. It's gummy, it hardens if you look at it wrong. Why is high-feed milling the solution here? I would think you'd want to go very slow and careful with that kind of stuff.
Going slow in inconel is actually the absolute worst thing you can do.
Yes. Inconel work hardens. As soon as you hit it with a tool, the material right at the cut zone gets physically harder. If you are moving slowly, your tool is just lingering in that zone. You are trying to cut material that is actively fighting you and getting harder by the second.
You're hardening it before you can even cut it.
Exactly. The high feed strategy, and specifically the Healy-Do feed system mentioned in the text, uses that speed to its advantage. You come in fast, you shear the chip, and you get out before the material has time to react. You are essentially beating the work hardening response.
You're using sheer speed to outrun the metallurgy. That is wildly cool.
It is. And for industries like aerospace, where they're making turbine blades, or the energy sector, this is non-negotiable.
Yeah.
You cannot have a tool fail halfway through a massive inconel part. The raw material alone is worth more than the machine sometimes.
So we've established it's fast, it's stable, and it cuts the uncuttable materials. But is it just a lawnmower? I mean, high feed sounds like it's great for facing off a big flat block, but can you actually make complex shapes with it?
It is definitely not just a lawnmower. The versatility is one of the most overlooked aspects of this whole system. The documents list a ton of capabilities beyond flat surfaces, pocket roughing ramping, and something called helical interpolation.
Okay, helical interpolation. That is a $10 term right there. Break that down for me.
Imagine you need to make a really large hole, say 4 inches wide in a solid block of steel. Conventionally, you might need a massive specialized drill. That drill requires huge horsepower and incredible torque.
And a really big machine just to spin it.
Right. But with helical interpolation, you take a small high-feed milling cutter, maybe only an inch wide, and you spiral it down into the material. It's orbiting in a circle like a planet while simultaneously moving down the z-axis.
So you're carving the huge hole out from the inside.
Yes. And because of the low axial engagement from that shallow cut, the load on the spindle is tiny compared to plunging a big drill. This means a small, light-duty machine can open up massive cavities that it theoretically shouldn't be able to handle at all.
Again, it's cheating the physics. You're doing very heavy work with a very light touch.
Exactly. And for mold and die work, where you have these complex 3D contours, curved surfaces, deep, intricate pockets, high feed milling is ideal. You can trace those complex shapes rapidly. The tool is small enough to get into the features, but fast enough to clear the material efficiently.
So is there ever a reason not to use this? If it's so magical, why do we even sell conventional end mills anymore? Should we just throw them all in the recycling bin?
Yeah. Let's not get ahead of ourselves.
Yeah.
The summary in the text makes a very clear distinction about when to use what. High-feed milling is specifically a roughing and semi-roughing strategy.
It's the bulldozer, not the paintbrush.
Correct. Because of the tool geometry.
Right.
That curved or angled bottom edge. High-feed milling leaves what we call scallops on the floor and walls of the part. It looks a bit like a plowed field. It is absolutely not a finished surface.
So you wouldn't want to try and seal a gasket against it.
Definitely not. For that final pass where you need a true mirror finish or a perfect clean 90-degree wall, you still need conventional tools. You need that long fluid engagement to wipe the part perfectly clean.
So the ideal workflow is you use high feed milling to rip out 90% of the material at absolute record speeds, and then you come in with a conventional tool for the last whisper cut to make it pretty.
Precisely. It's about choosing the right strategy for the specific phase of machining. Knowledge is knowing high-feed milling exists, but wisdom is knowing exactly when to switch out of it.
So what does this all synthesize into for us? We've gone from a 10-degree angle to the thermodynamics of chip evacuation to somehow revitalizing old loose machines.
If we connect all this back to the bigger picture, I think the core message from ISCAR is that efficiency isn't just about raw power anymore. For decades, manufacturing was just about more power, more rigidity, bigger motors.
The more power approach.
Exactly. But this research really highlights that we have hit a limit with brute force. The future of manufacturing is about geometry. It's about being smarter with the actual forces we generate. ISCAR didn't just make a sharper piece of carbide. They engineered the forces themselves to turn the enemy, which is heat and vibration, into something totally manageable.
I love that concept. You aren't fighting the metal, you're outsmarting it.
And that leads to a really fascinating thought for anyone listening. Whether you're running a massive 5-axis mill or honestly just trying to get through your own daily to-do list.
What's that?
We are so conditioned to think that deep work means digging in and pushing until we burn out. We assume that depth automatically equals productivity.
The conventional milling mindset applied to life.
Right. But ISCAR's success with this technology proves that sometimes the biggest gains don't come from pushing harder or digging deeper. They come from changing your angle of attack entirely. Taking lighter steps, but taking them relentlessly fast, can actually get you to the finish line sooner, and with way less wear and tear on your own personal machinery than the heavy lifting ever could.
Light steps, fast pace, better angle. I think that is a strategy we can all use, even if we aren't cutting titanium blocks.
Just remember to watch your chip thickness.
I'll definitely keep an eye on it. Thank you so much for walking us through this today. It's honestly amazing how much pure science is packed into a spinning piece of metal.
It was a pleasure to break it down.
And to you listening, next time you see a complex machined part, whether it's a jet engine component, a complex mold, or even just the aluminum casing of your laptop, think about the strategy that made it. Ask yourself, are you trying to cut too deep when you should really just be cutting faster? Thanks for joining us on this deep dive. We will see you next time.